this question can be pretty challenging or quite different than what you normally see in your paper 4. So let's read the question together. A sphere of mass 1.6 times 10 to the power of negative 10 kilograms. So we know that the mass of the sphere is pretty small, but I guess significant enough for them to tell us. Okay, and it has a charge of 0.27 nanocoulomb. The sphere is in a uniform electric field, so there is some E field here. Okay, so the electric field will interact with the charges, and this electric field is acting vertically upwards. So this is a side view, meaning you are viewing the setup from the front. Okay, and you have a bunch of electric fields pointing upwards, like that. And the sphere's charge is positive 0.27 nanocoulomb. So this is a positive charge. So by our understanding of electric fields, the direction of force exerted on the sphere by the electric field causes the sphere to maintain in a fixed vertical height in the horizontal plane. So I guess the question here would be to ask ourselves, what is this force exerted on the sphere by the electric field? I'm just going to call this the electric force with the symbol Fe. Okay, so we know that the direction of the electric field lines is the GPS for positive charge. Since the sphere is positive charge, we know that the direction of Fe will be here. So Fe must be parallel to the direction of E. All right, so this direction of field lines here is the direction of the electric force on a positive charge. Teacher, what happens if the charge is negative? Well, if the charge is negative, then you flip the direction. Meaning if I put an electron here, the electron will experience a force downwards. Okay, so this arrow, this GPS is for positive charges. Okay, let's say you forget during the actual exam. You go like, hey, I don't remember positive or negative charges. Well, another way to look at it is to visualize what sets up the electric field lines in the first place. To have this kind of uniform electric field, we need some parallel plates. So these two are parallel plates. And we know that the electric field lines will go from positive charge to negative charge plates. So where will the positive charge be attracted to? The positive charge will be attracted upwards towards the negative plate. But then the question says here that is to remain, this sphere is going to be fixed in a vertical height on a horizontal plane. So the sphere is actually here, it's fixed. All right. So then the question would be, why is the sphere fixed? Because it is in equilibrium. Fixed vertical height implies that the sphere is in equilibrium. At least in this case, it is in some form of vertical equilibrium. So there is an upward electric force pulling it up, but there has to be a downward force. Now, what would this downward force be? Weight. The weight of the sphere, which we can calculate using the equation mg. But you might say, Miss, I do the past year question, right? They normally ignore the weight acting on the charges. That's true. If let's say you are talking about one electron or one proton or maybe one helium, one alpha particle, we can more or less neglect the effects of gravitational field. But if number one, the mass is given, 10 to the power negative 10, then if you think about it, mass of proton is 1.67 times 10 to the power negative 27 kilogram. Negative 27 kilogram or negative, the order of negative 27, this one, we can ignore the effects of gravitational field because the mass is too small. In this case, the mass is pretty big compared to negative 27, okay? Negative 10 is still a lot bigger than negative 27, which is why there is still weight. So now, this mass tells me to also account for gravitational field. aka there is still weight acting on the sphere. All right. Okay, let's continue the question. So this one looks like it's in equilibrium. And then it carries on here to say that there is a uniform magnetic field. Wow, this question is a combo. They put all three fields together in one question just to mess with your brains. Okay, so this one, there is magnetic field in the region of the electric field, and the sphere moves at a speed of 0.78 in the horizontal plane. So a speed of 0.78 meter per second in the horizontal plane. Okay, you may be wondering, vertical is fixed, but if you view from the top, okay, so I'm just going to maybe use, I guess, my headphones as an example. So imagine this is my charged sphere, right? And this is horizontal. So the upward electric force and the downward weight balance each other out. So if you view from the side view, you will see this thing like this. But if you view from the top, it actually is moving in a circle. So if you view from the top, it's actually going this way. It maintains the same height, but actually it is oscillating forward, backward, or at least if you view from the top in the counterclockwise direction. Okay, yeah? So it is at the same height at around the level of my eyes, and then it's going to turn, turn, turn. So they decide to draw two views. View from the side, which is where you are looking at through the webcam now. This one is maintaining the same height. And then view from the top, you will see something like this. It is turning. Okay? All right, so if that causes confusion, always pause, maybe take an eraser or a pencil and then try to turn things around. You got this, okay? So right now, the magnetic field causes a sphere to move in a circular path with radius 3.4. So when we see circular path, okay, there are a lot of ideas here, you know. Circular path here means that there is centripetal force. So something needs to provide centripetal force. There has to be a force pointing in this direction to provide centripetal force. Okay, and we have the radius, so this is r. Let's highlight that. And the first part of the question, you're asked to determine the direction of the uniform magnetic field. All right, so to find the direction of this force, we know that the only force remaining, so we already draw gravitational force downwards, electric force upwards. If you view from the top, okay, so if this is my object or my charged sphere, if you view from the top, the electric field was pointing upwards, right? So if you view from the top, where is my finger pointing towards? Towards you. Okay, so once again, electric field is pointing upwards. If you view from the top, it's pointing towards you. Okay, so you can try and see, you can take some object and then you view from the top. Okay, anyway, that's why you can see the electric field lines is out of the plate, out of the page pointing towards you. Okay, so this is definitely not electric field, you know. And then at the same time, this is a positive charge. So this positive charge has a velocity in this direction. This is V. Okay, and this one will be the magnetic force FB. We've covered all the forces. There is electric force because there's an electric field. There is gravitational force, which is weight, which is mg. This electric force is QE. Okay, and now the final force is magnetic force. Okay, that's the only force that can possibly be here. All right, in fact, the question have given you enough hint. The magnetic field causes the sphere to move in a circular path. Centripetal force is provided by magnetic force, FB. Okay, so this is the direction of FB. Now, to find the direction of the magnetic field, we need to use Fleming's left hand. Okay, so your left and my left is inverted, okay, because of the camera. So if I use Fleming's left hand, FBI, okay, first thing I'll do is I'll point the direction of F, and I will refer to the bottom. So at this bottom one, the F is pointing upwards. Okay, F. Okay, and where is I? I is FBI. I is the middle finger. So the middle finger have to direct towards the direction of V. Okay, so if I point my thumb upwards and my eye is pointing to the direction of V, my magnetic field is actually into the paper. So the magnetic field, again, I'm going to use blue for this, is going into the paper. All right, so I will draw your Fleming's left hand. So try to align your left hand this way. This should be the direction of your thumb. This is a thumbs up. Okay, this is the direction of V, because this is a positive charge, so it's the same as the direction of I. This is your middle finger. All right, and if you do this, you will realize that your index finger is pointing into, okay, maybe I'll change color. Use red for this. Okay, so your magnetic field, this is your index or your pointing finger or your second finger, pointer finger, index finger is pointing into. If it's into, this one, into the page. This thumb is up, and this middle finger must be pointing from left to right. Left to right. Okay, so this is your Fleming's left hand rule. So learn to apply Fleming's left hand and understand that right now what we have is a magnetic field that is going into the page. So there is magnetic field going in and there's electric field going out. Okay, so if I look at this, this is the direction of electric field. This will be the direction of magnetic field. Opposite direction. Okay, one is going out of the paper, one is going into the paper. Okay, so yep, that's how we draw. And I guess for this direction of uniform electric field, you can say that it is, you can either say it is vertically downwards based on this picture, vertically downwards from the side view, or you could just copy this into the page. Part 2, explain why the motion of the sphere in the horizontal plane is circular. So we sort of have a hint on why this is circular in the first place. If you read back the question here, it roughly mentions that the magnetic field causes the sphere to move in a circular path. So which means the only force that can provide the centripetal force is magnetic force. So I think I will write that first as the what I like to call the lowest hanging fruit or the easiest thing to write. Okay, so I would say that the magnetic force on the sphere provides the centripetal force. But this is too, this is too straightforward. We also need to also talk about what exactly is the property of the magnetic force. So whenever you want to write explain, right? Don't just say there is a force. Basically ask yourself, what is a property? So what is a property or characteristic of that force that allows it to be centripetal force? It's a bit like, hey, explain why you got the job. Well, I got the job because I'm good, but what exactly about you that is good? So what exactly about magnetic force provides that centripetal force? If you think about the motion of that circle that is turning this way, every single point of the pathway, the direction of magnetic force is pointing 90 degree to V. Think of your Fleming's left hand rule. All these three things must be 90 degree, all 90 degree to each other. So FB is always 90 degree to velocity, because depending on where your pathway is, the tangential speed is like so. So all of this is 90 degree. All right, so that would be a property that's important. So the second point I will write here is that this magnetic force is perpendicular, or is always perpendicular to the velocity of the sphere, charged sphere, okay? And because it's always perpendicular, it doesn't change the magnitude of the velocity or doesn't change the speed. And doesn't change the speed of the sphere. What it changes is the direction, but the speed, the value of V is always the same. Okay, part B. Calculate the strength of the uniform electric field. And the next part I just want to read here. By considering the magnetic force, show that the flux density of the magnetic field is 0.14 Tesla. So in this calculation section, whenever you encounter a paper 4 question, right, what we try to do, or what the paper setter try to do, is they try to provide a story for you. So if you look at this question, the setup is quite long. When I say setup, I mean like the information that they give you and the drawing that they give you so much information so that you have a proper brain to think about what is going on. Okay, so when you want to calculate, all the hints are already inside the question. So for example, if I want to find the value of the electric field, okay, I need to think about like what is the reason why, or what's the role of the electric force. So the role of the electric force, as you can see here, the force exerted on the sphere by the electric field causes the sphere to remain at a fixed horizontal height. So this one is the role of the electric force. Question already tell you, okay? Meaning you can already say that the electric force will balance the weight. All right. And the second thing about questions like this is sometimes they will ask you to explain something, and it's hoped that inside this explanation, explain why it moves in a circle, you can actually tell that the setup of the question sort of begin to make sense to you, because they're asking a question that is related to guide your thinking. So take a breath. Try to think along the lines of what they're asking you. Okay. So in this case here, the role of the magnetic force is due to the magnetic field. The magnetic field causes the sphere to move in the circular path. So as you can see, me writing FB equals centripetal force. So this is the role of the magnetic force. Okay. So from the role of the electric force balance weight, I can write Fe is equal to mg here. All right. So this one is because this is your charged sphere, your electric force is upwards, your weight mg is downwards, and then this one is what they call a side view. The first drawing. Okay. Then if I want to look at the magnetic force, the role of the magnetic force is for it to move in a circle. So this is your circular part, and this is your charged sphere. Maybe I'll put a different color for my circular part. There we go. This is your charged sphere, and the magnetic force is the one that is always changing direction, like this, 90 degree, 90 degree, and the magnetic force provides the centripetal force. Okay, so we're going to use this as a base for our calculation. Electric force can be calculated using this expression QE, because electric field is defined as electric force per unit positive charge. All right, so I can place mg here. To find electric field strength, it will be mg over q. I prefer to rearrange everything before substituting, so that I only need to press calculator once. So right now we know the mass, 1.6 times 10 to the power of negative 10. G is our good old 9.81. And the charge on the sphere is 0.27 nanocoulomb, so 10 to the power of -9. So if we press our calculator, we will get 5.81. I mean, this can be Newton per coulomb. So another way to know the equation, the question is trying to help you see. So when you see NC -1, it means that to find electric field strength, I will take force over charge. The unit corresponds. So sometimes the unit is actually quite helpful to help you recall some equations. All right, finally, let me double check. So all the values given to me are in 2 sig figs, okay? 1.6 is 2SF, 0.27 is 2SF. So for this one, it will be nice to follow the number or significant figure, 5.8. You want to add one also you can put 5.81, but this is good enough, 2SF, because the whole question is given values and data in 2SF. All right, part C. By considering the magnetic force on the sphere, show the flux density of the uniform magnetic field is 0.14 Tesla. So from here, magnetic force provides centripetal force. So if magnetic force provides centripetal force, FB is equal to FC. Meaning to say, I will have BQV, because this is the force acting on a moving charge, and this one will be MR. There are two choices. We can go with MR omega square, but let me double check the question first. So in the question, right, I have the radius, but I also have the velocity V, 0.78. Okay, so I think it's better to use the equation with the linear velocity V. So instead of MR omega square, I am going to stick with mv square over r. Okay, you want to use MR omega square also can, then you have to find omega. I don't like to do extra work, okay? So I would rather just stick to this. Okay, so we're going to simplify the equations a bit. So the V and V and V square and V sort of like cancels off. We're looking for B. So B will be equal to mv over rq. Okay, so we can now substitute. We have the mass, 1.6 times 10 to the power of 10. We have the speed of the particle given to us, 0.78. We also have the value of r, 3.4 meter, if I'm not mistaken. Let me double check. There we go, 3.4 meter here. Okay, and finally, the charge is 0.27 nanocoulomb. If you are super confident, you can just lay this down at 0.14. If you're not sure, you can always press your calculator. And the calculated value I have is 0.1359, which is equal to 0.14 Tesla when rounded to 2 sig fig. Okay, so these kind of questions, right, most of the time, sometimes people will memorize this expression. They will memorize this one. Okay, now if you memorize this, it's actually a bit dangerous because you can lose at least 1, if not 2 marks. Because the reason why this is 3 marks is not so much to see whether you can substitute the values or not. It's to see whether you understand the fundamental idea that the magnetic force provides a centripetal force. So this line or this line, so the shortest you can go is to start with this. This is 1 mark, B1. It means the student or the candidate has an understanding that magnetic force provides centripetal force. Okay, the second one is to rearrange so that you get your B. Okay, and then after that, what remains is the substitution. So to get 3 out of 3, you really have to start with magnetic force provides centripetal force, or at least BQV is equal to mv squared over r. Okay, so the examiner report is fairly clear about this. Key step have to be shown. All right, and also the substitution as well. So for this one is more straightforward. If you understand that the mg is equal to QE, this is C1, the substitution leading to your final answer is A1. Okay, so what have we learned in this question? Let's do a quick recap. In paper 4, whenever you see questions where the picture or the diagram or the setup looks new to you, tell yourself it's normal. Tell yourself you can do it. Because why? You've been learning all the physics ideas, so no big deal. Different drawing, same concept. The concept that we have used so far is, number 1, electric force. It's in the same direction as the electric field lines for a positive charge. So for this to move in a horizontal plane, okay, then the weight has to cancel off the electric force. Oh, this is equilibrium, like your AS, okay? And then once we know that it is on the horizontal plane, we also know that when viewed from the top, it will circle. It's going to go like this. Whee! Okay? So when it circles this way, what is going on is there is a magnetic force providing the centripetal force. Among your 3 fields, maybe this is why the question is seen as a bit difficult, because you have electric field, you have gravitational field, you also have magnetic field. FB is BQV. Okay, so since you have magnetic field is the only one that can guarantee this sweet 90 degree. There are so many clues or hints or tells here to show you that, hey, magnetic force is the one that makes it moves in a circle, because you really need that 90 degree. Okay, gravitational force can provide centripetal force only for planets or satellites or sun and earth or moon and earth. Okay, because moon and earth, then the attraction is 90 degree to the circular path. Let's say the moon is going this way. See? So we need that 90 degree, and in this case, the only thing that can do is magnetic field. And then what is remaining is just writing down the expression, okay? And also using the right forces, because different force will produce those different effects. Stay calm. Paper 4 is not straightforward, but it's also not so difficult that you cannot do. Believe in yourself. I'll see you in the next one. Bye.